time for us to do some problems involving chain rule. So we're doing a little bit different here. We're focusing on one very important topic, and it really is a nice, important topic. The chain rule of mathematics is one of the most important rules because one of the most common ways to put functions together is as functions inside of functions. So that means practice is very important. So we need to get good at doing these problems, and that means we need to do lots and lots of problems. If you're following along with the video, make use of the pause button. See a problem that you like? Pause it. Try it yourself first and see how far you can get. And if you ever need help or you want to compare answers, unpause, and away we'll go down our wonderful journey through math together. Well, let's begin. So our very first problem, nice warm-up. We're told, suppose z equals xy, x is a function of t, and y is g of t, and use the chain rule to find dz dt. Now this seems really, really super simple, and there's kind of a punchline. So let's bear with it and just talk about what's going on here. So what we have is we say, look, z is a function of x and y, and x and y are each functions of t. And our question is, well, how does z change with respect to t? So the way that we'd answer that was to say, well, look, dz dt is equal to, and we'll come here before we finish anymore and say, look, what you do is every time that you go down, there's a partial derivative. So z depends on y. So this edge would correspond to partial z, partial y. And the reason it's partial is there's multi-branches. In other words, this is a function of more than one variable. Then there's a dy dt. Over here, partial z, partial x. And here, dx dt. All right, so what we get is that dz dt. The way that z changes as we change t is we say, aha, there's t showing up in two places, and we work our way down. Partial z, partial x, dx dt, plus partial z, partial y, dy dt. That's first branch, second branch. So far, we've just written down the formula. Well, let's actually push it and see what happens. Partial z, partial x. Well, if I come here and I say, what's the derivative of z with respect to x? Well, derivative of x times y with respect to x is y. Derivative of x with respect to t. Well, we can write it as f prime of t. And then here we have partial z, partial y is what? Derivative of z with respect to y is x. And then times dy dt is g prime of t. But wait, let's do one more thing. We know what x and y are. So we could write this as g of t, because that's what y is, f prime of t, plus f of t times g prime of t. Now, does this look familiar? It should. What is this? It's the product rule. So we say, aha, this is great. This is the product rule for the functions of two variables, right? Because what do you see? It's derivative of the first times the second plus derivative of the first times the second, just sort of slightly rearranged depending upon how you say it out loud. So what does that say? It says, look, if you want, you could say, I don't need to memorize the product rule anymore. I just memorize the multivariable chain rule, and I can rederive it. No. That's not what we're saying. What we're saying is it's kind of this cool idea where all things weave together, and you get some very nice consistency and nice connections showing up. All right, well, that was a fun little practice. Well, let's do a little bit more fun practice, of course. Really, we want everything we do to be fun. So, our next problem. Given that z is a function, f of xy, and x is a function of two variables, s and t, and y is a function of two variables, s and t, find partial z, partial s, and partial z, partial t. So in other words, we're just trying to say, let's just sort of do a couple different things with the chain rule here. So what can we do? Well, we can say, what's happening? Well, z depends on x and y, because that's what it says. And then x and y are both functions of s and t. So this is the picture that's emerging about how things depend on one another. And then we can even go through and label everything if we wanted. So each edge going down is a partial derivative. So this is partial z, partial y, and of course I should have made the picture bigger because we're going to run out of space. But lo and behold, each edge corresponds to a dependence, right? How does one variable depend on another variable? And so we can say there's a derivative attached to each edge. So each edge, what is it? Well, you say, how does this depend on that? Partial x, partial s, as an example. So if we want to talk about the partial derivatives, and note here, notation thing going on. We are using the partial symbol. We're saying partial z, partial s, and partial z, partial t. And the reason we use the partial symbol is we say ultimately when you get down to the very bottom, how many variables are showing up? Well, there's two, s and t, which means that our function z is dependent on two variables. So it is a multivariable function, which is why we use the partial symbol. But once you have the structure in place, the tree, you can read off the answers. So, for instance, partial z, partial s, well, you just say, find all the places where an s shows up and work your way down. Each way is going to be a different term. You add them up. So there's through x, so that would be partial z, partial x, partial x, partial s. So that's the way you can think of it is, how does s affect z through x? Add to that, and then you go the other route down. Partial z, partial y, partial y, partial s. And then if we want to ask now with respect to t, and of course, similar thing, we say, look, partial z, partial t, again, two things. We'll have a partial z, partial x, partial t, and a partial z, partial y, and a partial y, partial t. And what we're doing is we're just going down. So boom, boom, multiply those partial derivatives together. Boom, boom, multiply those partial derivatives together, and so forth and so on. You can do all sorts of fun things. And once you understand, look, things can be more complicated. You can have all sorts of ways that the variables connect together. But at the end, everything just works out. Just say, look, whatever you're taking the partial derivative with respect to, figure out how to get from the top down to where those variables are, and multiply as you move down. And for each one of the variables, you add up all the pieces together, and there you go. So in some sense, it's really super easy. So there's not that much to the chain rule. It's just, you just do it, and life is good. So, wonderful. How hard could it be? Well, it could be a little bit challenging at times. We'll do some problems which will definitely be like, I think the hardest part will be, and we're among friends now, so we can tell this to each other. Honestly, it's the notation. If you can get past the notation, life is great. Okay. This is not a notation problem yet. Those will come up later on. So, here we go. An adjustable can machine has the ability to alter the dimensions of cylindrical cans as they are being produced. The gauges currently read as follows. H equals 5, dV/dt equals minus 6 pi, dRdt equals minus a half, and dH/dt equals 1, where VHR are volume, height, and radius. The gauge for R is broken. And the question is, Well, what could R be? What are the possible values for R? Okay, interesting. Well, let's see if we can figure this out. So we say, okay, it's a cylindrical can, which means our can looks like a cylinder. All right, so great. So what's the important thing about cylinders? Well, you have the height, and of course you have the radius, r. And the volume is pi r squared. That's the area times the height. So area on the top or bottom of the can times the height of the can. That gets us the volume. Life is good. Okay. On the other hand, we have things that are changing with respect to time. So the radius is changing, the height is changing. So what's going on here is we have the following scenario. We see volume depends on R and H, and R and H vary with T. So that's our setup. And so we can say, all right, how does volume change with T? So we run it through and say, all right, dV dt is, well, T shows up twice. We're going to go through R, so that would be partial V partial R times dr dt plus, then through H, partial V partial H times dH dt. Well, all right, let's clean it up. Well, what is partial V partial R? Well, if we come up here, take the derivative with respect to R, we'll get 2 pi RH. We have dr dt. Take the derivative with respect to H, pi r squared dH dt. Wonderful, wonderful. Well, now let's plug in what we know. That's often a time, right? We get to an expression, plug in what you know, solve for what you don't. It's a wonderful way to approach problems. So, do we know what dV dt is? Yes, negative 6 pi. All right, so negative 6 pi equals 2 pi. Do we know what R is? No. If we did, it wouldn't be a problem because we're looking for R. R. Okay, how about H? Yeah, we know that. It's 5. dr dt? Yeah, negative half. Okay, plus pi r, still don't know that, squared, dH dt? 1. Beautiful. Well, let's see, what can we do here? Well, certainly we can cancel the pi's, because every term has a pi. So divide out, get rid of the pi, pew, pew, pew. And it looks like it's an equation just in R. Actually, it's a quadratic equation in R. So what do we have? We have R squared, okay. Then we have 2 times minus a half times 5. That would make it minus 5r. Then there's a minus 6. We'll bring it across as a plus 6. Is that equal to 0? Well, that factors. R minus 2, R minus 3. And either one is reasonable because we can have either 2 or 3 as the radius. So those are our two settings, 2 or 3. So we don't know which one. There's 2 possibilities. That's all right. If one of them had been negative, then we could say, well, it can't be the negative one. So in this case, there were possible values. There was 2 of them. Now you might pause and say, this feels vaguely familiar, almost like related rates. Okay, it actually is related rates in a sense. So when we were doing related rates, we were kind of running through what was happening with the chain rule. Now, so how did it become the chain rule? Well, you see, what happened is when we had related rates, we said, okay, we're going to replace everything by the functions. So we didn't think of this as R anymore. we thought of this as r of t, and we didn't think of this as h. We thought of it as h of t. And then we said, okay, now we have everything as functions of t, and away we go. So what the chain rule did is said, okay, well, we're just going to think of them as r and h, not necessarily as functions of t in the initial formula. And then the next layer says, okay, now they're functions of t. But the important thing is, either way, we get the same answer. The process is very similar. All right, well, good. These are great. We're going to be done in hardly any time at all, right? Well, maybe. Let's try another one. Given that f of xy is everywhere differentiable, that means we can take derivatives wherever we want, and f of t squared minus 2t, comma, e to the t minus t is this really bizarre expression. Something. All right. Then there is one point for which f sub x can be determined exactly, and there's a different point for which f sub y can be determined exactly. Determine these points and the corresponding partial derivatives. So it feels like how? What? And at first glance, it doesn't seem like we can make much progress. But of course, we don't just go off of first glances, right? So let's think about what's going on here. So if we dig into it a little bit, we say, all right, think of this in the following way. This is f t squared minus 2t e to the t minus t. Well, I can write e to the t minus t equals e to the 3t minus sine of 2t plus t squared. This t squared minus 2t is acting like our x. This e to the t minus t is our y, and then of course we have our z. So if we're thinking this as z is a function of x and y, well, we would normally say, look, z depends on x and y, and x and y now are functions of t. Okay, well, that's not so bad. Nothing too exotic here. So if we just write down the chain rule without really thinking too much, we come to the conclusion, well, dz dt, so I want to know how does z change with respect to t, I've got to go two paths. So there'll be two pieces. I say, what is the partial z partial x? So boom. And times that by dx dt. And I'm going to add to that partial z partial y. And I'm going to multiply that by dy dt. All right. Well, we're going to just go through each one of these pieces. So let's start with dz dt. Well, what is dz dt? Well, we actually can write it down because we have z as a function of t. So we say, all right, 3e to the 3t, then minus, derivative of sine is cosine, so 2 cosine 2t. The 2 shows up because of the chain rule. And the derivative of t squared is 2t. So that's the dz dt equals partial z partial x. Okay, what is partial z partial x? Well, we're thinking of z as being f of x, y. So partial z partial x would be take the derivative with respect to x. And the way we would denote that is we'd say, okay, take the derivative with respect to x would be our f sub x, right? Okay, now, what do we write? Well, we would write f sub x of x comma y. Well, we know what x and y are, so we're going to go ahead and put those in as functions of t. So t squared minus 2t, e to the t minus t. Now, so that's partial z partial x. dx dt, so take the derivative of x with respect to t. We're going to get 2 times t minus 2. Plus, now we're going to do the same thing, partial z partial y. Well, z is a function f of xy, so partial z partial y is f sub y. You're going to write in what x and y are as functions of t, times dy dt. So take the derivative, and we're going to get e to the t minus 1. Okay, so now we have this expression. Okay, and at this point, we're starting to get a little bit nervous, like, we don't know what f is. We haven't even talked about that. And we'll never know. It's impossible for us to know. There's not enough information. But that's okay. We can still answer the question, even if we don't have enough information. So, where to go from here? Well, we want to say, look, we want to solve for f sub x at AB, which means if I want just f sub x, what should be true about f sub y? I don't want it to be there. So now we come to this and say, is there some value of t which makes this 0? So that's our sort of question. Can we do it? Well, we don't know anything about the f. We don't know anything about f sub y. But we do know about e to the t minus 1. Is there a good choice for t so that e to the t minus 1 would equal 0? Well, if you choose t equal 0. And so, say, okay, great. Choose t equals 0. Then what happens? Well, what happens is we're going to get the following. E to the 0 minus 1 is 0. That term is gone completely. What do the rest of the terms become? Well, we're going to get 3 e to the 0. Okay, that's not so bad. Okay, so let's just work it out. T equals 0. We're going to get 3, then minus 2, okay, and plus 0 equals, and then here it's going to be f sub x at 0 minus 0, that's 0, and then it's going to be 1 minus 0, 1, and then 0 minus 2 times negative 2, which leads us to conclude f sub x at 0, 1 is, well, 3 minus 2 is 1, divided by negative 2, negative a half. And that's part of our answer. We now know exactly that at the point x equals 0, y equals 1, it must be the case that f sub x equals negative a half. It must happen that way. We have no choice. And now we're emboldened to say, okay, cool, we're going to just repeat the process and say, okay, let's choose a t to make this 0. Why? Well, because we want to find something which has an f sub y. Okay, well, let's think about it. Again, we don't really know a lot about f sub x, so not a lot of hope to make that 0. But 2t minus 2, there is hope to make that 0. What's a good choice for t? 1. Cool. Okay, great. So now we're going to plug in t equals 1 and see what happens. Well, we're not going to get quite as nice of numbers, right? Well, but we're going to get numbers. We'll get 3e cubed minus 2 cosine of 2. And cosine of 2, also known as cosine of 2. Yeah, it doesn't simplify. Well, such is life, plus 2 equals. Okay, this term goes away. So then we have f sub y, and 1 squared minus 2. That's negative 1, comma, e to the 1 minus 1, e minus 1, times, okay, e minus 1. Okay, there we go. So, what does that tell us? Well, it tells us the following. Namely, we can solve, say, look, fy of minus 1, e minus 1. I just need to divide that across. So we get, and I guess the hard part is going to be squeezing this in, 3e cubed minus 2 cosine 2 plus 2 all over e minus 1. And there we go. We got it on, just barely, but it's all there. It's all there. and we're done, right? Because we said, look, there's some place where we can completely determine f sub x. It's at 0, 1. There's some place where we can completely determine f sub y. It's at -1, e minus 1, and we know what those values are. And wow, probably once we saw the answer for f sub x, we're like, wow, this is beautiful. F sub y will surely be just as nice. Well, sometimes it doesn't work out that way. That's all right. That's all right. Good. On to our next problem. Okay, whoop, here we go. So, suppose that f of xy is differentiable and satisfies f of t cubed minus t plus 1, comma 2 minus t squared is this expression. T to the fourth minus 4t cubed plus 4t plus 6. Find f sub x at 1, 1 and f sub y at 1, 1. In other words, we're going to find the partial derivative with respect to x and y at the point 1, 1. And so that's kind of cool. Now, before we begin, let's talk about what we can't do. Some people approach this problem and say, well, we just have to figure out what f is, and then we're good to go. And so they say, well, let me try to see if I can find a function f that does what I want to do. And they come up with functions that almost do that. Here's the thing is, we cannot find f. It's impossible. You do not have enough information to reconstruct f. Now, what you can do is you can find an f for which it's true, but that doesn't mean that you'll actually have done the problem, because it's not enough to say, oh, here's one problem or one possibility and it works in that one possibility. Because, well, what if there's a different possibility? Would it still work? And you'd be like, well, I'd have to check. That's not a satisfying answer if you have to say, well, maybe, I don't know, I'd have to check. We want to say, look, regardless of what f is, there really are infinitely many possible f that have this relationship. There's a lot more that don't, but there's infinitely many that do. And we don't want to say, well, we did check this one, but I didn't check all the infinitely many others as well. So we are not going to find f. This is not a, ooh, let's find f and see what happens. And so you might say, well, how can we do it if we don't have f? And I'll tell you, there's something else that's really, really interesting about this problem. Where we say, well, we're going to find f sub x and f sub y at the point 1, 1. And it turns out 1, 1 is the only place where we can do it. You can't do it anywhere else. And that seems sort of counterintuitive. It's like, why not? Why couldn't we do it anywhere else? So I want to talk about what's going on in this problem and why we have a hope. Okay, so what do we have? Well, if we think about it, let me write this down again so we can label things. So we have f of t cubed minus t plus 1, comma 2 minus t squared equals t to the fourth minus 4t cubed plus 4t plus 6. And we can think of it in the following way. Well, what we have is an x and a y, and we can think of this as our z. And if you look at this curve, because you really do have a parametric curve, you have x is a function of t, y is a function of t. So if you think about this as, well, this is a parametric curve of sorts, what does it do? Well, what happens that makes this interesting is it has the following shape. It comes up in some way and it crosses over itself. And I drew my picture very poorly, but this crossover point, that's going to be important. I claim that this is at the point 1, 1. It's the fact that it crosses itself twice says, hey, you actually have two chances to gain information about what's happening. And so that's why we have an opportunity to gather two pieces of data about what's happening at that point. Now, let's actually figure out if this is accurate. Now, don't worry about the actual shape, but let's see about the claim that it passes through the point 1, 1 on 2 times. Well, suppose we think about it and say, okay, we're trying to find times t where I pass through the point 1, 1. Well, that says y has to be 1. So when does 2 minus t squared equal 1? Well, that's the same as saying t squared has to be 1, which says t has to be 1 or negative 1. All right, so that's when we'll definitely have the right y value. Now we just have to check that the x value matches as well. Well, if you plug in 1, 1 cubed minus 1 plus 1 is 1. Negative 1 cubed is negative 1. Subtract negative 1 cancels. Plus 1 is 1. So we say, aha, this is sort of the great aha. We are at time plus minus 1. So remember, we're just going to be 2 times. Now, what's the other thing that we're going to do? Well, the other thing we're going to see is that we have chain rule. What tells us chain rule about this problem? Other than, oh, but this is the chain rule, right? This is our session. Now, everything is chain rule. Remember, you might see a problem out in the wild, and you might say, well, what is that problem doing over there? What is it trying to achieve? The way we recognize chain rule is when we have, say, a function inside a function. So we see like this t cubed minus t plus 1 is a function inside a bigger function. And also same thing with 2 minus t squared. It's a function inside a bigger function. And therefore we say, aha, this is chain rule saying functions inside of functions, and we're ready to go. So chain rule tells us, if we think about our picture, z depends on x and y are functions of t. So we can say dz dt is equal to partial z partial x dx dt plus partial z partial y dy dt. So far, no big surprises. And we can actually fill in all our pieces. dz dt, well, that would be the derivative of this side. That's 4t cubed minus 12t squared plus 4. Okay, that's it. Just take the derivative. Equals partial z partial x. Well, that's f sub x, right? Because we're thinking of it as, where do we have it? Well, we didn't write it down anywhere. So we'll write it down over here. Z is f of x comma y. So that's f sub x of, instead of writing that all out again, I'll just say x of t comma y of t, just shorthand, times dx dt. Well, okay, plug in dx dt, take the derivative. That would be 3t squared minus 1. And then partial z partial y, that's f sub y. And again, xt y of t, that's just a shorthand way of saying these pieces here, times dy dt, which would be minus 2t. Okay, at this point, we say, now we care about the 2 times plus 1 and minus 1. So let's plug those in. So we're going to plug in at time t equals 1. Now, I'm going to do this side first. When we're at time t equals 1, we're at the point 1, 1. So what we get is we're going to get fx 1, 1 times 3 minus 1 is 2. So I'll just put the 2 here. 2 times fx at 1, 1. And now, similar, we get fyy at 1, 1. Okay, because that's where we're at, times negative 2 times 1. So minus 2 equals, now you plug 1 into here. 4 minus 12 plus 4. That's what? So let's say minus 12. Negative 4. Good. Good. Now, that's one time. Plug in the other time. At time equals -1. What do we have? Well, again, we're at the same point. We're at the point 1, 1. So we're going to get fx at 1, 1. And now when we plug in 3 times -1 squared minus 1, now we're going to get still 2, right? Because the square doesn't really do anything different. We're still at 1, 1, so we'll have fy at 1, 1. Minus 2 times -1, though, is something interesting. It's now plus 2. So that's a plus 2. And that'll equal what? Well, plug in -1. So you get -4, -12, -4. That makes -20. All right. Great. Wonderful. Good stuff. Good stuff. Okay. So, what do you have? Our bread and butter. 2 equations, 2 unknowns, and now we just put them together and solve. In fact, they were very nice to us, really nice, almost like they wanted us to succeed. Because what can we do? Well, we can add. If we add these together, what happens? The f sub y's will cancel, and we'll get 4 fx at 1, 1 is equal to -24. Okay, which tells us f sub x at 1, 1 is equal to -6. Now, what else could we have done? Well, we also could have subtracted if we wanted to. If you subtract, so 2 minus 2 goes away, then you get -4 fy at 1, 1. -4 minus 20 is positive 20. It gets you to 16. And that tells us that fy at 1, 1 is equal to 16 over -4 is -4. And therefore, we're done. We found fx at 1, 1, -6, and fy at 1, 1 is -4. Woohoo! We did it! We did it! Ah, good times. Great times, really. We were able to figure it out. And was there a secret? Something that made it work a little bit nicer? Well, I don't know. Wait a second. Did we do this right? I'm worried about t equals -1. Let's see. When we plug in -1, we get -4, -12, plus 4. Oh, no. It shouldn't be -20. It should be -12. I'm so sorry about that. Okay, so when we combined them here, that should have been -16, which means that this is really a -4. Oh, I feel bad. Okay. And when we subtract, -4 plus 12 makes this an 8. And so this should have really been a -2. Okay, all right. Other than our silly algebra mistakes, okay, other than those, which of course, we make them, it's not so bad. It's sort of we play around with it and we follow it through, and it comes out. I really love this problem. And there's actually more than one way to solve this problem. You can solve it in multiple ways, but that's a different story. So I won't tell that story. For now, we're satisfied. We found the solution. All right. Well, good. On to more problems, right? Of course. Let f of xy be a differentiable function, and g of xy is f of x squared y, comma xy cubed. And given that at the point 1, 1, the tangent plane to g of xy is something, z equals 7x plus y minus 4, find the tangent plane at 1, 1 to f of xy. Okay, interesting. Well, what do you know? Well, we have to think about this a little bit. Not too much, but enough, right? So what we need to do is to think about what we have. So there's this basic rule of thumb which says the following, which says if I have a tangent plane at a point AB, then what that tells me is I really have some pieces of information. And what I have is, well, let's say our function, let's call it h. I have what the value of the function is, what the partial derivative of the function is at that point with respect to x, and what the partial derivative at that point is with respect to y. So we can think of our tangent plane as storing three things about our function: its value and the value of its two partial derivatives. So we want to say, okay, what we want to do is figure out what's going on. Now, for instance, let's talk about the fact that we know a tangent plane to G. So what does the tangent plane to G tell us? Well, it tells us the following. So we have our G of x, y at the point 1, 1. Well, it tells us we must know what G of 1, 1 is. We must know what G sub x at 1, 1 is. And we must know what G sub y at 1, 1 is. Well, let's write these down. So in theory, we should just be able to look at the plane and be able to doon, 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 doon. Well, we can if it's written in the form z equals. And it is, so that's good news for us. So the partial derivative with respect to x is what's in front of the x here, but you have to have z equals to do this. Okay, so that says g sub x at 1, 1 is 7. G sub y at 1, 1, read the coefficient, it's 1. How about g of 1, 1? Well, to figure that out, plug 1, 1 into here. So what do we have? We'll have 7 plus 1 minus 4. So g of 1, 1 is 4. All right, so there we go. That's the information that we have. And our goal is to say, well, okay, let's find f at 1, 1, f sub x at 1, 1, f sub y at 1, 1. If we can find these things, then we have a hope. Okay, so let's just note that one of them is pretty straightforward. Which one? Well, I'll go ahead and finish our thought process here. This would give us the tangent plane to f of x, y at 1, 1. So we'll actually do the computation that gives us that tangent plane as we approach the end. So first off, we know what g of 1, 1 is. So g of 1, 1, we'll plug in 1, 1 over to here. That's equal to f of 1 squared times 1, 1 times 1 cubed. That's f of 1, 1. But we know g of 1, 1 is 4, and therefore we say, look, this is also 4. Okay, we're a third of the way there. Ha-ha! Woohoo! Progress! Well, of course, that means 2/3 remaining. But I want to be the optimist and be like, wow, we were a third of the way. Woohoo! Isn't it better to always look on the bright side of life? Always look on the bright side of life. Now there's a hint. It says use the chain rule, right? Okay, so we're saying, hey, we really have g. It's a function of u and v, and u are functions of x and y. So it says, think about it in the following structure, where g depends on u and v, and u depends on x and y, and v depends on x and y. So where they actually say what u and v are. So let's do that. Okay, so we can say the following. We can say g sub x. That's partial g partial x is equal to what? Well, we're going to take g, which really is this function f of u comma v. We're going to take the derivative of that with respect to u. All right, well, what would that be? Well, it would be f, see, the u is in the first slot. So when we think of u as being in the first slot, we write that as the x slot. That's just our notational convention here. And I'll just put what it is, x squared y comma xy cubed. So that's the derivative with respect to u times the derivative of u with respect to x. So times the derivative of x squared y with respect to x, which is 2xy. Add, now we're going to come through this other root. When we take derivative with respect to v, that's our second slot. We'll call that f sub y, x squared y comma xy cubed, times the derivative of v with respect to x. The derivative of xy cubed with respect to x is y cubed. So there we go. That is what g sub x is. And now we say, well, let's plug in what we know. We know what's happening at 1, 1. So we can say, look, 7 equals g sub x at 1, 1 equals, well, that would be f sub x at 1, 1 times 2 plus f sub y at 1, 1 times 1. So that's nice. We now have an equation involving f sub x at 1, 1 and f sub y 1, 1. So we've narrowed our search down a bit. But we're not done yet. Okay. The other thing, of course, is repeat the process g sub y. Well, what would that do? A similar process, right? We just follow it down. So the derivative of the function with respect to u, first layer, that u shows up in the first slot, so f sub x, x squared y, x y cubed, times the derivative of x squared y with respect to y would be x squared, plus, now we went that way, next is this other branch. So derivative of the function with respect to v, that v shows up in the second slot, the y slot, so fy, x squared y, xy cubed, times the derivative of xy cubed with respect to x, which is 3xy squared. Plug in 1, 1, so we plug in what we know, and we say, okay, g sub y at 1, 1 is 1. All right, so that tells us what? Well, that's f sub x at 1, 1 times 1 plus f sub y at 1, 1 times 3. Good. Well, perfect. This is the kind of thing that we love. We love problems like this because we have two equations now. These two equations. We'll write them down one more time and we'll say, hey, let's figure out what we can do to solve. So we have fx times 1, 1, and there's a 2, so I'm just that term, plus fy at 1, 1 has to equal 7, and then fx at 1, 1 plus 3fy 1, 1 has to equal 1. Well, two equations, two unknowns. The bread and butter of calculus. We should be really comfortable with doing these types of problems. So, for instance, if we take the first equation and subtract 2 times the second equation, you'll see that the fx at 1, 1 terms cancel. What do you have here? Well, you have 1 minus 6, which gives us negative 5. Fy at 1, 1 would be 7 minus 2, which is positive 5, which says, lo and behold, f sub y at 1, 1 is equal to negative 1. Well, that's fantastic news. So now we know what f sub y is. We can plug it into one of the formulas. So for instance, we can say f sub x at 1, 1, this term, plus 3 times negative 1, which is minus 3, equals 1, which says, oh, fx at 1, 1 has to equal 4. So we know these two values, 4 and negative 1. Now, we've figured out the function at 1, 1, partial derivative of x at 1, 1, partial derivative of y at 1, 1, which means we have the tangent plane. Well, really it means we have the information to make the tangent plane. So the last part of the problem is we have to find the tangent plane. And we know that we have to do that because it tells us find the tangent plane. Okay, good. So we have to just do it. Well, let's do it. So we get the following. We're going to have our tangent plane. Well, it's the z equals f1, 1 plus fx at 1, 1, x minus 1, fy at 1, 1, y minus 1. That's just the generic formula for the tangent plane at 1, 1, and we just plug in what we know. So we end up with z equals 4 plus 4 times x minus 1 minus y minus 1. Right? Because I plug in 4 for f1, 1, 4 for f sub x at 1, 1, and minus 1 for f sub y at 1, 1. Well, we can clean that up. So that says z equals 4x minus y. You have a plus 4, a minus 4, and a plus 1, which should make this plus 1. And we're done. That's it. That's it. That's the answer. Wow. Cool. It's a really clean answer. 4x minus y plus 1. You wouldn't have probably said 7x plus y minus 4 doesn't look like 4x minus y plus 1. That's why, of course, we did the work. We were able to figure out how can we get from there to there. And the key is that ability to hop back and forth. Hey, tangent plane means I've got some information. Let me figure out new information. Let me get my new tangent plane. Ah, what a great problem. Lots of fun. Lots of fun. Cool. Well, let's keep going. So, our next problem. Given that f of xy is this expression, okay, and the following information, determine the tangent plane to f of xy at the point 3, 1. So this is sort of testing us on like very pure, do you know the chain rule? Because we're not going to give you any functions. What we're doing is we're storing the information in a table format. So it's just giving you enough information, plus probably a lot to distract you, because you look at it and say like, there's so much information here. Do we really need all of it? And the answer is probably no, not really, but you will need some of it. And so part of it is figuring out, well, which information will give us exactly what we need to figure it out. So let's think about what's going on here. We have the following, right? We have our function, which, well, what can we say? We'll put it here. Our function, I'll call it z, initially depends on two variables, u and v. So he's like, okay, so it depends on u and v. But they also depend on x and y. So we get a nice little diagram of our dependencies here. So we have to figure out, okay, how does this all fit together? Well, and the other thing, of course, is how do we get the information to make our tangent plane? Well, what we need to make our tangent plane is we need three things. We need to know what's the value of the function. In other words, what is f of 3, 1? What's the value of the derivative, f sub x, at 3, 1? And what's the value of the other derivative, f sub y, 3, 1? So in other words, we need to know the partial derivatives. If we know these three things, we can write down our answer. Life is good. It's going to take us a while to get there. Now, one of them will actually be pretty quick. Let's talk about f of 3, 1. Because, according to the rule, let's just do that. See what we get. That would be, let's not make it too messy here. So f of 3 comma 1 would be g of u of 3 comma 1 comma v of 3 comma 1, right? Because we're just literally plugging in x equals 3, y equals 1. No big surprises. So now comes our chance to say, let's start looking things up. So we say, okay, we need to know what is u of 3 comma 1. Well, we say, okay, so we're at the point 3 comma 1, and we come over to the column for u. So we need that information. That is u of 3 comma 1. So we say, great, that's g of 1 comma, how about v of 3 comma 1? So again, we're at the point 3, 1, and we come to the column for v. Say, okay, that's that piece of information. 4. So v of 3 comma 1 is 4. So hey, if I want to know what's happening to the function at 3, 1, I need to know what is g at 1, 4. So let's figure that out. All right, well, we're in luck. We have a 1, 4, and that corresponds in our column for g to 1. Good. So success. Okay, so we now can say we're a third of the way there. We found what happens to the function at 3, 1. Woohoo! Nice! All right. Well, that was maybe the easier third, I suspect. Let's dig into some of the more interesting thirds. All right, so let's tackle the partial derivative with respect to x. What can we say? Well, we can say the following, that f sub x, when I'm taking the derivative with respect to x, is what? Well, just if we follow it here, I can say, look, x shows up in two places. So I'm going to take the derivative with respect to the first slot, which is called g sub u, times the derivative of what's in the first slot, u sub x. And then I have to take the derivative with respect to the second slot, g sub v, times the derivative of the second slot with respect to x, v sub x. I'm really coming down along this diagram. So this, for instance, is g sub u. Here is g sub v. This would be u sub x, u sub y, v sub x, v sub y. So that's just it in a very compressed notation. Well, okay, let's dig into it a little bit. Now, what happens? Well, we plug in 1, 1. So what do we have? We have fx at 1, 1. Well, that's good. That's what we want to know. Is g sub u at, okay. Now let's see if we can figure out what goes inside. If we think back to our chain rule, and if it helps, think back to single variable calculus, way back. Oh, we were so young back then. Wow, how the time has gone by. But if you think back to that, you said, remember, when we're taking the chain rule, you don't change the inside. So when we're plugging in x and y equals to 1, we're really plugging in the inside of g looks like that. So it's really u of our point, sorry, not 1, 1, I'm sorry, where did I get 1, 1 from? 3, 1, 3, 1. I think my mind was stuck on a previous problem. So when we plug 3, 1 in, we're really saying, oh, the inside is still the same u and v. So it'd be u of 3, 1, v of 3, 1, which we already know corresponds to the point 1, 4. And then we're going to have u sub x at 3, 1. And then we're going to have g sub v. Again, it's g sub v, but we're still going to have the u and v being going into it. So g sub v at 1, 4, and v sub x at 3, 1. Okay, so that's what happens when we plug in 3, 1. I think these two people are going to be happy with. These two are like, wait, what? So let me try one more time. I'm trying to compress because I want to not have to spill onto a second page. But of course, in my efforts to compress, I unfortunately might have ended up obfuscating a little bit more than I intended to here. So when we write G sub u, remember that's just a shorthand, I'll put it down here, of G sub u of xy, v of xy. So that's really what's being represented by this G sub u. And so when you plug in 3, 1, it's G sub u of 3, 1, v of 3, 1. But we've already computed u of 3, 1 and v of 3, 1 as 1 and 4. All right. Now we go back to our table. And we start saying, okay, let's find what we need in our table. And hopefully it's all there. Well, yeah, it's all there. Otherwise, the problem couldn't be done. Well, so we need G sub u at 1, 4. Well, oh, right there. It's negative 4. Okay, so that equals negative 4. U sub x at 3, 1. Okay, so 3, 1, u sub x, oh, there it is, 7. Okay, so negative 4 times 7. G sub v at 1, 4. Okay, that's 7. Oh, okay, that's all right. Plus 7. And v sub x at 3, 1 is over here. 3, 1, v sub x is 6. So 7 and 6. So what do we end up with? Well, minus 28 plus 42 gets us to 14. All right, so there we go. Progress, right? Yes, it is. It is progress. Cool. So that goes here. Now we have to turn and say, what about f sub y? Well, once we've done the f sub x, the f sub y is going to feel very similar. Okay, so again, think about getting down to the y's. There's 2 of them. So we have f sub y would be g sub u, u sub y. All right, that's reasonable. And then g sub v, v sub y. All right, great. Now, plug in. So we're going to get that fy at the point 3, 1 is equal to g sub u at the point 1, 4 times u sub y at the point 3, 1 plus g sub v at the point 1, 4 times v sub y at the point 3, 1. Okay, well, that would be equal to, well, g sub u at 1, 4 still is the same as before. It's still negative 4. That doesn't change. So negative 4. U sub y at 3, 1. Well, oh, here it is. U sub y at 3, 1 is 2. So negative 4 times 2 plus g sub v at 1, 4, still 7. That hasn't changed. V sub y at 3, 1. Well, that's that part right there. So that's 3. Okay, so we have minus 8 and plus 21. And if you put those together, what do we end up with? Well, we end up with 13. Okay, great. So that says f sub y at 3, 1 is 13. Perfect. Now we're ready to write down our answer. So what do we get? Well, we get the following. We can say our tangent plane is of the form, we take our function at that point, 1 plus 14, which is our derivative with respect to x, times x minus our x value, plus 13, our derivative with respect to y, times y minus our y value. And that's it. That's our answer. Now, if we wanted to, we could push a little bit more and simplify and say, look, this is the same as z equals 14x, because you can multiply the 14 through, plus 13y. And now, well, do a little bit of math, a dangerous thing in our head. Well, maybe 14 times 3 is 42. It's the answer to life, universe, everything. 13 times 1 is 13. So we have minus 42 minus 13 would be minus 55. All right, plus 1 makes that a minus 54. All right, good. Now, you might be wondering, which is the right way to write the plane? You notice I'll circle this one. It actually depends on what you're doing. And in some sense, I'm sort of doing the wrong thing. It really, in several applications, it's much better to rewrite it in that form, especially when we're trying to understand things such as how do things change with respect to one another, and so forth and so on. But for right now, either is fine. Now, you might leave this wondering, okay, why did we not use most of this? And the answer is, well, oftentimes we'll do this with problems where we're going to give you a lot of information. And what we're really doing is we're trying to understand, can you see what's important? It happens frequently in real world problems where you're like given way more information than you could possibly ever need or possibly ever use. And in that case, you have to figure out which pieces of information are the important pieces, which ones give you what it is that you need to understand. And there we go. Life is good, right? Life is great. What a fun problem. What a good fun problem. All right. Well, let us do some more good fun problems. Well, if you liked the chart one, but thought, boy, it'd be nicer if there was a smaller chart. Be careful what you wish for. We're going to do this one, and this is probably, if you want to be confused, this has the best chance. If you can't get confused on this one, I don't know if there's much that can confuse you. Okay, so what's going on here? We're going to create this function g of xy, which is f of, and in the first slot we put an f of xy, and in the second slot we put an f of yx. So we do the little switcheroo. Ha ha, whoop, woo-hoo-hoo. Okay, so what we've done is we've really built g up out of f, but we've kind of put f together in a weird Frankenstein-like manner. And here we are like, and so we have to really, really pay attention. So here's the thing we want to be careful of. You'll see it here with the notation that we have. Notice we don't use x and y, we just say s and t. And we say f sub s, f sub t. And I really want to point something out here, because if you can capture this with the notation, then everything else that we're going to do, you're going to say, okay, I'll buy into it. And if you can't capture it, you're going to be a little bit lost. And here it is. Really, what this is telling us is which slot we're taking the derivative with respect to. So this says f sub s of s, comma t says I'm taking the derivative in the first slot. So the f sub t, s comma t says I'm taking the derivative with the second slot. And so if you keep that in mind, we'll be okay. And hopefully by the end, we're all on speaking terms with one another. Oh, of course we'll be. We'll be fine. We'll be fine. We're all friends here, right? We're all friends. So let's get a handle on this. We know where we're going. We need to find a tangent plane at the point 2, 1. So let's make some notes here. So we need to find g of 2, 1, g sub x of 2, 1, and g sub y of 2, 1. And once we find those, then we can write down the formula for our plane, and we're good. So let's start with the g of 2, 1. That one seems the most straightforward. So according to the rule, we have g of 2, 1 would be, so that's saying x equals 2, y equals 1, f of 2, 1, comma, f of 1, 2. So it's one of these onion things. We have layers. What is f of 2, 1? Well, f of 2, 1 is 1. So we need this slot. So that's f of 1, comma, and f of 1, 2, well, that's here, 3. So f of 1, 3, and we say, aha, f of 1, 3, we know that, it's right here. That's negative 1. So, one term down. Progress. Really progress. We've gone and done something. Now, we're going to do our partial derivative. Okay. We're just deep breaths, deep breaths. We got to relax and just calmly work through it. Now, let's start by taking the derivative with respect to x. And where does it show up? So I'm going to use s and the t just to remind ourselves. When I say s, first slot. When I say t, second slot. When we're doing the derivative with respect to x, it shows up in two places. So here we go. So g sub x of xy. Well, there is an x in the first slot, so I take the derivative of the outside function with respect to the first slot, but I don't change the insides. Chain rule says the insides stay alone. And now, times that by the derivative of the inside with respect to x. Here, where does the x show up? It shows up in the first slot again. So that's f sub s of xy. Plus, okay, now I go to the fact that it showed up in our second slot. F sub t. The insides still are what they are. But now I'm taking the derivative of the second slot with respect to x. Where does the x show up? It shows up in the second slot. So f sub t of y comma x. Okay, good. Okay, now let's plug stuff in. So we can say g sub x of 2, 1. Well, this f of 2, 1, f of 1, 2, we already know it's going to become 1 and 3. So it's f sub s at 1, 3 times f sub s of 2, 1 plus f sub t. And again, these, when we plug in 2, 1, it's the same thing as when we plug in 2, 1 up here, which means it's going to become 1, 3 again. So f sub t at 1, 3 and f sub t at 2, 1. All right, so what does we have? Well, we start looking things up. fs at 1, 3, well, that's right here. So that's 2. F sub s at 2, 1 is here. That's negative 1. F sub t at 1, 3. Okay, that's here. That's negative 3. And then f sub t at 2, 1. That's here, and that's positive 3. So we have 2 times negative 1, negative 3 times 3. Put them together, we get negative 11. So, negative 11. Good. All right. So we have our g sub x at 2, 1. Now we're going to repeat the same process, but do it for g sub y. But of course, once you do it once, the second time should hopefully be not so bad, right? Same ideas. So we get g sub y of x comma y. Well, we say, look, y shows up in both slots. So take the derivative of the outside with respect to the first slot, f of x comma y, comma f of y comma x, times the derivative of the first slot with respect to y. Well, now, notice where is the y? It's in the second slot, so it's going to be f sub t of x comma y. Plus, now go take it, the derivative of the outside with respect to the second slot, f sub t, f of x comma y, f of y comma x, times the derivative of the second slot with respect to y, and now it shows up in the first slot, which means it's f sub s of y comma x. Okay, so we're ready to plug in 2, 1. So what do we have? Well, it's fs still at 1 comma 3 times ft at 2 comma 1. And then ft, again, 1 comma 3, fs at, here it's going to be 1 comma 2. Whoops, I can see we made a mistake in the previous line. We should fix it. When we plugged in 2 comma 1, we put 2 comma 1, but what it should have been? It should have been, let me make it a color so I can correct myself. Like I said, this one will make you go crazy trying to keep track of things. So if you can get through it unscathed, it should have been 1 comma 2. So we need f sub t at 1 comma 2. So we really need this value. So that's a negative 1. So it's not 3 here. This should have been a negative 1. So we have minus 2. Here it's plus 3, which means it's actually really simple. Minus 2 plus 3 makes it positive 1. Okay. There we go. All right. Good. Well, I'm glad we got it right eventually. It's better to get it right before you turn a problem in. Okay. Well, now let's go through and be careful. Okay. F sub s at 1, 3, still 2. That hasn't changed. F sub t at 2 comma 1. So f sub t at 2 comma 1. Look, we still needed it. So that is 3. All right, great. And then plus ft of 1 comma 3 still is negative 3. That's not going to change. Fs at 1 comma 2 is here, and that'll be a positive 1. So you get 6 minus 3, which leaves us with 3. All right, so that is 3. Good. You know, on a side note, we put this on an exam, and the students were not very excited about this particular problem for some reason. We're almost done. We're almost done. Again, you can see we used not everything that was given to us. They gave us some sort of red herrings mixed in, just so we were paying attention. But that's okay. Oftentimes when they give you a chart, it's very rare that you use the whole chart. So we're now ready to put it all together. So what's our answer? Well, we need a plane. So we have our data. So our tangent plane would be our function at 2, 1 plus our g sub x at 2, 1 times x minus 2 plus our g sub y at 2, 1 times y minus 1. Well, what is that? At our function at 2, 1, negative 1 plus g sub x at 2, 1 is 1 times x minus 2. And then g sub y at 2, 1 is 3 times y minus 1. So if you clean that up, we get z equals x plus 3y. And then let's see, we have a minus 1, a minus 2, and a minus 3. So minus 1, minus 2, a minus 3, put them all together, minus 6. And that's it, right? Yeah, that's it. Z equals x plus 3y minus 6. What a great, beautiful answer. Wow, wow. Well, if you can do this problem, you're in amazing shape, great shape. And just, it's all about patience, following through, working with your notation, and then you're fine. You can do it. You can do it. All right, well, I think we should do one more, right? One more. And here we go. All right. Well, if you were worried, we were like, where can we go from there? Well, we can go this way. You are given that the functions f of xy, g of xy, and h of xy are differentiable everywhere. And we have a lot of tangent planes. So a ton of tangent planes, an amazing amount, a cornucopia, if you will, of tangent planes. We're going to create a new function called k. K of xy is f of g of xy comma h of xy. And we want to find the tangent plane at 1, 2. And we want to give our answer in the form ax plus by plus cz equals d. And there's a hint. You don't need all of the information in the table above. Well, that's probably a good sign because there's a lot of information going on in our table above. Okay, so what are we going to need? Well, we think about our basic facts, and one of the basic things we know is if we're looking for a tangent plane, we need 3 pieces of information. So we need to figure out the following. What is k of 1, 2? What is k sub x at 1, 2? And what is k sub y at 1, 2? And if we know these things, then we can find our plane. So we're going to fill in this chart, we're going to write our plane, and life will be good. Let's start with the value k of 1, 2. What are we going to need? Well, let's just start to get an idea of where we care about things. So when I'm looking for k of 1, 2, that's the same as f of g of 1, 2, comma h of 1, 2. All right, so if I want to know about g of 1, 2 and h of 1, 2, I should look at the tangent plane to g at 1, 2 and the tangent plane to h at 1, 2, which says I need to look at these pieces of information. Here, g at 1, 2, sorry, that's h at 1, 2, and here's g at 1, 2. Okay, so we have those planes there. Now, we want to rewrite these planes to make them a little bit more friendly. How will we do it? Well, for this plane, we really want to have it in the form z equals something. So let's move the z and the 5, have them swap places. So I'm going to add z to both sides, add 5 to both sides. And if we do that, I'm going to turn this a little bit sideways here. So what do we have? We have z equals 2x and minus 2y and plus 5. Okay, so that's the tangent plane 2G at 1, 2. We're going to do the same thing here. Well, it's going to be even easier. We just move the z across. And what does this say? Well, it says z equals 3x plus y. Okay. So, with this in mind, we really say, aha, we can read off information because these planes are storing information. So we can gather what the functions are doing at the points. So what's happening to g at 1, 2? So in order for me to know what g at 1, 2, I say, okay, I have my tangent plane at 1, 2, and I plug in x equals 1 and y equals 2. So that would become 2 minus 4 plus 5. 2 minus 4 is negative 2, plus 5 gets us to 3. Okay, so that says g of 1, 2 is equal to 3. Okay, how about h of 1, 2? Well, we come into this plane, that's our h of 1, 2. We plug in x equals 1 and y equals 2. 3 plus 2 is 5. So that's f of 3 comma 5. Well, which tells us we need to know what's happening to f at 3 comma 5, which says we care about this plane here. Okay, so that's the one we care about, and we'll do the same treatment. We'll move the x and the y across, and this would tell us z equals minus x plus y plus 2. All right, so minus x plus y plus 2, we plug in 3, 5, so it's minus 3 plus 5 is 2 plus 2 more gets us to 4. So k of 1, 2 is 4. All right, well, that's not so bad. Good. We're a third of the way done. Well, that means 2/3 to go, but we're at least making progress. We feel good. And we've already started to identify, hey, these are the important things. So let's go on and talk about k sub x. Well, we can see chain rule, right? Because we have functions, g and h, inside another function, f. So we would say, look, k sub x of xy will have f sub x, which really means the derivative with respect to the first saw, because we're thinking of f of xy. So that would be fx g of xy comma h of xy times the derivative of the first saw with respect to x, g sub x of xy, plus, okay, now the second slot, fy, and, oh dear, we're going to run out of space. So I'm just going to put in, I'll put a dot, 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 comma, dot, dot, dot. So for these pieces here, just so we have enough space, times the derivative of the second slot with respect to x, which is hx, xy. Okay, plug it in. So k sub x at 1 comma 2 is equal to, well, when we plug in 1, 2 into here, we're going to get 3, 5, right? G of 1, 2 is 3, h of 1, 2 is 5. So that's f sub x at 3, 5 times g sub x at 1, 2. And then there's going to be an f sub y at 3, 5 again, times an h sub x at 1, 2. Well, we can read these off. F sub x at 3, 5. Well, that's the coefficient for x here, negative 1. G sub x, well, we go to where g is. That's this one. Read off the coefficient for x. That's 2. F sub y at 3, 5. Okay, that's the coefficient for y. That's a 1. And then h sub x at 1, 2. Come down here and read off the coefficient for x. That's a 3. So we get a minus 2 plus 3, giving us 1. Okay, good. Well, progress. Now, repeat one more time. Okay, so once more to the breach, dear friends. Once more. So, this one is going to feel really familiar. K sub y of xy. Well, no surprise. Okay, so we come here. Y shows up in both slots. So we're going to take the derivative of the outside with respect to the first slot, fx of the inside, times the derivative of the inside. And here we're going to do it with respect to the second slot. So g sub y of xy. And then plus, okay, now take the derivative with respect to the second slot, fy. Now take the derivative of the second slot with respect to y, and that would be hy of xy. Plug in. So, what do we see? We see k sub y at 1, 2 equal to f sub x 3, 5 times g, whoops, yeah, no, that's right, fx g5, 3, 5, gy at 1, 2 plus fy 3, 5 times hy at 1, 2. All right, well, we plug things in. So f sub x at our point 3, 5, still negative 1. Okay, so negative 1. G sub y at 1, 2. Well, okay, so we come to g sub y at 1, 2, negative 2. Plus, all right, now we talk about our next slot, fy at 3, 5. Well, the coefficient is 1, so 1. And then hy at 1, 2. So h sub y at 1, 2 is 1. So it's 2 plus 1, also known as 3. Great. Beautiful numbers. Beautiful. Almost as if whoever wrote this had planned them to be beautiful numbers. I think they did. All right. Well, we're almost there. We're in the home stretch. We have our data that we need to make our plane. So the last thing to do is actually just write down the answer. So our plane would be z equals k 1, 2 plus k sub x at 1, 2, x minus 1, plus k sub y at 1, 2 times y minus 2. Well, so that's 4 plus 1 times x minus 1 plus 3 times y minus 2. And if we clean that up, that's x plus 3y. Then we have 4 minus 1 minus 6. Well, 4 minus 1 minus 6. Minus 3, right? Sounds good to me. So 4 minus 1 minus 6 minus 3. Z equals x plus 3y minus 3. What an answer. What an answer. Now, we were really squeezing in what we did here. Normally, we would have tried to spread it out a little bit more, but we didn't have a lot of space this time. And so we tried to use up all of our real estate. But the important thing is, we said, look, when they're giving us tangent planes, it's the same thing as giving us a chart of data. The only thing is that instead of a chart, it's all being stored in these coefficients. And so it's the same process. Like, okay, let me figure out how to read off the data from the tangent planes and then piece it all together. So it's not that it's a hard problem, it's just you have to be very patient and very methodical, work it from beginning to end, and then you can get your answer. And what a process. What a process. And, well, these problems can be fun. Just be careful. If you were following along today, you saw many times today I made small mistakes because it's easy to get lost. If you're getting lost, take a step back and say, okay, hold on. What am I taking derivative with respect to? What should be going where? And oftentimes you can correct yourself. Because as, of course, the great philosophers would say, you must check yourself before you wreck yourself. Well, thanks for coming and doing all the practice. Hope to see you again soon. Bye.